Okay, so it's my pleasure to present Andrea Mondino from Oxford. Last week he gave a nice series of lecture on the RCD spaces. You can look at it on the platform. And today we will talk about timelike Ricci curvature lower bound via optimal transport in Lorentzian synthetic space and applications.
Thank you very much for the introduction. Thanks very much for this opportunity. So yeah, last week we talked about Ricci curvature bounds using optimal transport tools in a Riemannian setting and then in the non-smooth metric setting, which is kind of the non-smooth extension of the Riemannian smooth framework. Today, I would like to present an approach to kind of extend this kind of ideas to the Lorentzian signature. Okay, so we will start from the smooth Lorentzian framework, and then we will move to a synthetic Lorentzian framework and study their synthetic curvature bounds from below on the timelike Ricci tensor. Okay, so let's start with some. Yeah. Okay, so the aim, as I was saying, is to present some synthetic timelike Ricci curvature bounds for Lorentzian spaces, and we want to do it in low regularity because there is some motivation that I'm going to discuss in a moment to study Lorentzian metrics with low regularity, and these curvature bounds are going to be formulated in the language of optimal transport. So the plan of the talk is to start with some motivations and the general setting. And then we'll discuss some basics of optimal transport in the Lorentzian setting, and I will discuss things in a way that makes sense in a synthetic setting, so in a non-smooth Lorentzian signature. Then I will discuss smooth and synthetic curvature lower bounds on the Ricci, so and more specifically, you are going to see on the timelike Ricci. And then finally, I will discuss some applications to comparison geometry and Hawking singularity theorem. So all the work that I'm going to, all this project is joined with Fabio Cavalletti from SISSA. And if you're interested to see more details, you can see the paper in the archive. Here is the reference. Okay, so the general goal of the talk is the following. So as I hope that I convinced you last week in this series of lectures, optimal transport revealed to be a very effective tool to study spaces with extremely low regularity in Riemannian signature. So more precisely, as we have seen, one can use optimal transport to define and study metric measure spaces with Ricci curvature bounded below by some constant k, and dimension bounded above by some parameter n, and these spaces have these bounds in a synthetic sense using optimal transport, and this corresponds to the celebrated theory of CDK spaces of Lott-Sturm-Villani. Now, motivated by the success of this theory of CDK spaces, we aim to develop some optimal transport tools in a low regularity Lorentzian setting and develop a kind of Lorentzian CD theory. Okay, so we would like to introduce some kind of Lorentzian CDKN spaces. Okay, as a byproduct of this program, one will get some geometric and functional inequalities and some singularity theorems in a synthetic setting, which will include Lorentzian metrics of very low regularity. So this setting, as we will see, will include local ellipsis metrics, or more generally, continuous metrics, which satisfy some natural and nice causality condition, which is called causality plane in the literature. And as application, we are going to see some volume comparison, parameter bounds, Poincare inequalities, and the Hawking singularity theorem in a synthetic framework. Okay, now why use optimal transport tools? So if you have followed the last week course, probably you already know, but let me just refresh it for the people who were not present last week. So what we expect is that apart from the specific synthetic framework and the specific result that we obtained so far in the Lorentzian setting that I'm going to discuss in a minute, we we expect that the optimal transport tools in the Lorentzian signature will be useful in a wide range of applications. And why this? Well, because typically classical arguments in comparison geometry or in singularity theorems make use of Jacobi field computation that in the Lorentzian setting goes under the name of Ricci-Anduri equation. And such computation heavily rely on the C2 regularity of the metric. With some effort, one can lower the regularity to C11 by approximation. This is already a bit heavy, but it is quite hard to go lower than C11. So the main advantage of optimal transport is that basically it permits to carry over arguments which classically make use of Jacobi field computation in a setting of very low regularity where the classical terms do not even make sense. They are not even well defined. For instance, if you have a local Lipschitz metric, or even more generally, a C0 metric with some causal property, then you cannot write the Ricci tensor. The Jacobi fields are not really well defined, and so these kind of computations are really out of hope. But the main message is that the optimal transport tool can be helpful because you can kind of morally mimic some of the arguments, but with completely different technical tools. Okay, which makes sense in a very low regarding setting.
There is a question in the chat. What is the Ricci-Anduri equation?
Okay, so this is for people who know Lorentzian geometry. If you don't know the Ricci-Anduri equation, this is basically this is what the people in Lorentzian geometry call Jacobi field computation. Okay, so if you have never seen it, just think of in the Riemannian setting, you have the Jacobi equation on the you have the length-minimizing geodesic, then you perturb the geodesic with length-minimizing geodesics. This gives you some Jacobi fields. You want to, and then you can write down a differential equation for the Jacobi field, which involves the Ricci curvature. This is in the Riemannian setting. This is known as Jacobi field equation. In the Lorentzian community, these kind of arguments are known as Ricci-Anduri equation. Okay.
Another one.
Yeah. What does plane mean? Yes, this is right. I'm going to discuss it in a moment. If you have never seen it, just think of a local Lipschitz metric. The point is that when you consider C0 metrics in the Lorentzian setting, they do not behave very nice from the point of view of causal structure. So Crucial and Grant made an axiomatization. So they added some assumption on the metric. Basically is about the cylindrical, you want to find the good cylindrical coordinates in the causal cone. Is a bit technical, so I don't want to enter into the details. It is, so basically the message is, if the Lorentzian metric is at least Lipschitz regular, then it has a kind of nice causal structure, and you can do things almost as it was smooth. If you go below Lipschitz, you enter into the, say, if you go in C0, then you can have this so-called causal bubblings. For instance, if you are in the Minkowski space, the boundary of, say, the light cone is a codimension one object, so it is really a cone. And this is what happens also in local Lipschitz metrics. When you are in C0 metrics, it may happen that the light cone has non-empty interior. And this is called causal bubbling, and you want to prevent that because this is a kind of pathological behavior that the light cone has a non-empty interior, and to avoid that, you add this assumption called causal plane. Okay, it's a bit technical, but the idea is just to avoid that the light cone has non-empty interior. Okay. All right, so okay, So this is the overall advantage is to go in a low regularity setting. Now, why one would like to go in a low regularity setting in the Lorentzian framework? Let me discuss some motivation. So the first motivation comes from the Einstein equation. So we all know it, but let me just fix some notation. So let's consider an n-dimensional manifold. So typically the physical dimension is n equal to 4. So 4 is 3 dimension of space and 1 dimension of time. Endowed with the Lorentzian metric G. So what is a Lorentzian metric? It is a non-degenerate, symmetric, bilinear form of signature minus plus plus plus. Okay, so the plus 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 correspond to the 3-dimensional space direction, and the minus correspond to the time direction. Now, on a Lorentzian metric, one can write down the Einstein equation, which has this form here. So the Einstein equation involves the Ricci curvature, the scalar curvature, the metric itself with a constant lambda, which goes under the name of cosmological constant, and then you have the right-hand side, which say morally plays the role of source of gravitational field, and is the so-called energy momentum tensor that serves to model the matter present in the universe. Okay, now the necessity for Lorentzian metrics of low regularity comes from the PDE point of view, from a point of view of initial value problem for the Einstein equations. Indeed, one can write down this Einstein equation for, say, C2 metrics. But actually, in order to solve them as a Cauchy evolution, the natural thing to do, as in most of the PDEs, is to work in Sobolev spaces, so not in smooth spaces. All right, and then another necessity for Lorentz metrics of low regularity comes from physically relevant models. Indeed, there are models from physics where the stress energy momentum tensor T is discontinuous, and so if T is discontinuous, it means that also G is discontinuous. So G is below C2. G is non-smooth. Okay, and an example of this situation are the so-called impulsive gravitational waves, which were pioneered by Penrose, and there is some more recent work by Lorentzian and others. Okay, so there are physical models where the metric is non-smooth, and also from the PD point of view, it is natural to consider non-smooth metrics. And then in the direction of Einstein equation, let me mention that there has been a recent formulation of the Einstein equations in the language of optimal transport by McCann, who successfully characterized the non-negative Ricci in the timelike direction, and by myself and Suhr, who were able to characterize the full Einstein equation, so both lower bound and upper bound, and also with any cosmological constant and any stress energy momentum tensor. Okay, but I don't want to enter into that today. I would like to focus on the lower bounds. Okay. Then another motivation in order to study metrics of low regularity comes from the celebrated Penrose strong cosmic censorship conjecture. So this conjecture says roughly that for generic initial data, I mean Cauchy initial data for the evolution of the Einstein equation, the maximally globally hyperbolic solution, so you start from a Cauchy datum, you evolve it using the Einstein equation until it is globally hyperbolic, so until it is deterministic out from the Cauchy datum. Okay. Now you consider this maximal extension as globally hyperbolic space, and you ask yourself if this space is also inextendable as a Lorentzian space without asking global hyperbolicity. Okay, so the rough statement is, for generic initial data, the maximal global hyperbolic solution is inextendable as a suitably regular spacetime. And of course, you may have different answers if you ask, is it inextendable as a C2, or as a C0, or as a C1, or as a, say, C0 with derivatives in L2, something like that. Okay, there's a huge literature about this problem, which goes also under the name as extendability, inextendability property problem for space-times in low regularity. And here, let me just mention some key names. So, in addition to Penrose, there are deep results by Christodoulou, Dafermos, Kleinerman, Luke, Rodniansky, Zbirsky, and many others. Okay, and here it is key that this extendability of the space-time can take place at a lower regularity than C2. So typically, what one asks is C0 or local Lipschitz or C0 with Christoffel symbols in L2, so that the Einstein equation makes sense, but you want to go below the C2 threshold. Okay, so how this big problem connects with our framework? Let me just give you an example, one example of a possible application of our methods. Okay, so assume that you are given a space-time, MNG, which satisfies, say, the vacuum Einstein equation, possibly with some cosmological constant. So Ricci is constantly equal to some lambda. You can take also lambda equal to 0 for the sake of this example, and assume that you can extend this maximally globally hyperbolic space-time to a larger space, M tilde. This M tilde is with low regularity, so maybe it is a C0 metric, but it still satisfies, say, at least the lower bound, so Ricci bigger or equal than lambda in the timelike direction. Notice that if you take lambda equal to 0, you're asking that the initial space-time satisfies the vacuum Einstein equation, and you are asking that the extension satisfies the so-called strong energy condition of Hawking-Penrose, which is a kind of natural condition. Okay, and thanks to what I'm going to discuss in a moment, this lower bound, this Ricci bigger or equal than lambda or 0, if you want, makes sense basically without regularity assumption on M tilde. And this is what I'm going to call in a moment the timelike CD lambda n condition. Okay, so you start from a smooth manifold, this M. You assume that you can extend it to a larger space with very low regularity. With the optimal transport tool, you are able to say what it means for the extended space to have lower bound on the timelike Ricci. Okay, this is a physical reasonable assumption which corresponds to the strong energy condition, and then you want to say what kind of properties this enlarged space satisfies. Okay, so which kind of geometric analytic properties can we expect from the extension M tilde? Okay, and why we're interested in this kind of properties? Well, because we can use such properties in order to infer that maybe such extension cannot exist at all. So for instance, if the initial space M is kind of too bad near the boundary, so near the boundary where near, say, the boundary means that when you see it as an open submanifold in the extension M tilde, then maybe you cannot have such an M tilde with lower bound on the Ricci. For instance, if you are able to prove an isoperimetric type inequality, this will give a lower bound on the area of the boundary of M, say if the boundary of M is space-like. And then if you know that the boundary of M has too little area, then it cannot be extended in a larger space. And so you would kind of prove in this framework a kind of Penrose conjecture of strong cosmic censorship, because you are able to say that your manifold is not extendable because it has too small area. Okay, so this is kind of one possible way that this kind of results could be useful in the GR community. Okay, just an example. Okay. Now let me fix some basics of Lorentzian geometry, and then we are going to discuss the non-smooth setting. Okay, now we are given Mn, a Lorentzian manifold. now fix an auxiliary complete Riemannian metric H on M, and we are going to call dH the associated distance. This is kind of in the background in order to fix the topology of M, but since it is not the physical datum is mg, we want to do everything in terms of mg and just having a kind of nice topology in the background, which will not enter into the main statements. Okay, and in order to do that, we fix some auxiliary metric H. Okay, now we say that a tangent vector V is timelike if GVV is less than 0, and this comes from the fact that G is of Lorentzian signature. Okay, then we say that M is time-oriented if it has a continuous timelike vector field. So you're orienting kind of the timelike vector field with this continuous vector field. This Y is inducing a partition on the set of all timelike vectors into two equivalence classes. One is the future pointing, which are the ones with negative scalar product with this vector field Y. So notice that since Y is timelike, GYY is less than 0, and so Y is future pointing by definition. And then the past pointing are the ones which have scalar product strictly positive with Y. So they are kind of pointing in the opposite direction of Y. Now we call C the closure of the set of future pointing timelike vectors. So these correspond to the cone of causal vectors, union 0, okay, which are the kind of physical direction which are allowed to particles and to the light. Okay, now we say that a curve gamma, which is absolutely continuous from 0, 1 to M, is said to be causal if the velocity is almost everywhere in the causal cone C, and is timelike if the velocity is in the interior of the cone. Okay, so the interior of the cones are those vectors with G with the scalar product with themselves strictly less than 0, while the elements in the cone are the ones basically with G of themselves less or equal than 0. So they are the causal cones, causal vectors. Okay. Now these causal curves induce a causal relation. This is all very classical. So 2 points X and Y in M are said to be causally related and X less or equal than Y. If there is a causal curve starting from X and ending in Y, and 2 points X and Y are timelike related with this notation X less than Y, if there exists a timelike curve from X to Y. Now, once we have a causal curve, we can define its length in analogy with the Riemannian framework. But now, since it is causal, then G gamma dot is less or equal than 0. So when we want to take the length, we just take minus G of gamma dot under square root. Then we have the so-called time separation function, which plays the same role of distance, of Riemannian distance in the Riemannian setting. Here is the analog. So this is called tau. Is a map from m times m into 0 infinity, and given 2 points X and Y, which are causally related, is defined as the sup of the length of all causal curves joining X to Y. Okay, so notice that in the Riemannian setting, when you do the distance between 2 points, you take the infimum of the length of the curves. Instead, in the Lorentzian setting, due to the signature, you take the sup instead of the length of the causal curves. Okay, and then you set it to be equal to 0 if X and Y are not causally related. Now, a key property in the Lorentzian setting, which is a very strong difference with the Riemannian setting, is that this time separation function satisfies a reverse triangular inequality. So in the Riemannian setting, the distance satisfies, of course, a triangular inequality. the tau function, the time separation function, instead in the Lorentzian setting, satisfies the reverse triangle, which means that you just switch the inequality. But this is a very big difference. So this is a huge difference, and this also creates a lot of issues when you do optimal transport. Okay. Now a key property is that this time separation function tau is lower semi-continuous and is bigger than 0, is strictly bigger than 0, if and only if x is timelike related to y. So this condition is key for everything that we want to discuss. It's true in quite low regularity. So if the metric G is smooth or it is local Lipschitz, in general, for C0 metrics, is not true. Because of this, as I was saying before, because you may have this causal bubbling, you may have this, you may have that the causal curves minus the timelike curves span an open set, and this creates problems. And so you add some assumption, which goes under the name of causally plane, which was introduced in a paper by Crucial Grant. So I invite you to see this paper, which is very nice and important for the causal structure in C0 regularity. Okay. Okay, so this is a refresh of the smooth setting. And now, as we have seen last week, so last week what we did is we started from the Riemannian setting, and then we introduced these metric measure spaces as a kind of natural analog, a natural non-smooth extension of Riemannian manifold. Now we want to do the same. So we start from Lorentzian manifold, I just discussed them, and we want to do kind of synthetic, non-smooth extension of Lorentzian manifolds that goes under the name of Lorentzian prelength spaces. So the basic come from a beautiful paper of Cronheimer and Penrose in '67, who kind of axiomatized the notion of causal space. Okay, so a causal space is a set X endowed with a preorder less or equal. A preorder is something that is reflexive and transitive, and a transitive relation less, which is included in the less or equal. Okay, so the less or equal. So we have in mind that this less or equal is the causal relation, and this less is the timelike relation. So actually, the classical paper of Cronheimer and Penrose ask some additional properties on this less or equal and less, but here is an adaptation from the paper. And as I was saying, we say that X and Y are timelike related if X less than Y, and they are causally related if X is less or equal than Y. Okay. Now we want to introduce, so this is kind of the underlying, this is in order to axiomatize the underlying causal structure. Now, when we do Lorentzian geometry, not just the causal, we need also the time separation function. We want to axiomatize it. This has been done in a quite recent paper by Kunzinger and Seemann, who introduced this notion of Lorentzian prelength space. So a Lorentzian prelength space is a causal space in the sense above, so X with a timelike and causal relation, endowed with a proper metric X, which is a kind of underlying metric fixing the topology, and a lower semi-continuous function tau from x times x into 0 infinity, called the time separation function, and which will play the role of time separation function of the previous slide, such that xy is equal to tau of xy is equal to 0 if x is not causally related to y, and tau satisfies this reverse triangle inequality as before, and tau is bigger than 0 if and only if x is chronologically related to y. Okay, so this is kind of, here you are axiomatizing basically what we saw before for a kind of local Lipschitz Lorentzian metric. Okay, now what happens is that under only this assumption, you can basically run the causal machinery, and you can define all the natural causal relation. So we say that a curve gamma is said to be timelike if it is local Lipschitz, and if gamma of T1 is chronological to gamma of T2 for any T1 less than T2, and gamma is said causal if instead gamma of T1 is causal to gamma of T2 for T1 less than T2. Once you have a time separation function tau, you can define the length associated to a curve gamma in basically in morally the same way as when you have a distance, you have a notion of length, kind of length space structure, kind of pre-length space structure associated to the distance. So in the Riemannian, in the metric setting, what you do is you take partition of intervals, and then you do the sup of the distance between elements of this partition. And this is because in the Riemannian setting, you take the inf of the length. Here in the Lorentzian setting, you take the sup of the length, and so instead of taking the sup over the partition, you take the inf over the partition. So in this setting, the length induced by tau is the infimum of overall partition of the interval of the sum of the time separation function among elements of this partition. Okay, so you have a well-defined notion of length, and then you say that a causal curve gamma is a geodesic if its length is equal to the time separation function of its endpoints. So in complete analogy with the metric setting. Okay, now let me recall some notions of causality. If you're not too much interested in that, I will just give you an example, and then you can fix your ideas on the example. But let me briefly recall it because technically they are quite useful in our framework. Okay, so we have this Lorentzian pre-length space. We said that it is causally closed if the subset in x times x given by the points which are causally related is a closed set, closed subset in x times x. Then another important property is the non-totally imprisoning, which says that given any compact set in X, there exists a positive constant such that the length of all causal curves contained in the compact set is bounded. Okay, so why this should be true? So in the metric setting, this is just false because you can have curves which are kind of oscillating. Here, why it is true? It is true because basically the curves which are causal are forced to stay within the cone. So they have a privileged direction which is going up in time, and so they cannot oscillate in a crazy way like in the Riemannian setting. Okay, so this is a kind of natural condition which is satisfied, for instance, for local Lipschitz metrics. Okay, then you say that your space is globally hyperbolic if it is not totally imprisoning, so this condition up there, and the so-called causal diamonds are compact. So a causal diamond means if for any 2 points, x and y, you take the future of one point intersected with the past of another point. So the picture is that of a kind of 2 triangles, kind of a diamond, and you ask that this is compact. Then we ask the k-global hyperbolicity, means that you ask the same, but not just for points, but for any compact set. So the future of any compact set intersected with the past of any compact set is compact. And then you say that your space is geodesic if for any 2 points which are causally related, there exists a geodesic joining them. Okay. All right, now, as I promised, the example. So if you have a locally Lipschitz metric over a, say, C2 spacetime, which is globally hyperbolic in the classical sense, then the induced synthetic structure has all these nice properties. Then the induced structure is causally closed, k-globally hyperbolic, and geodesic. Okay, so this framework includes all the locally Lipschitz and globally hyperbolic metrics, and more generally, it includes the continuous metrics, which are causally closed, which are causally plane, and globally hyperbolic. So it includes a kind of quite large class of Lorentzian metrics of low regularity. Okay, so this is the general setting, and now we would like to do optimal transport in these spaces. Okay, so we have this Lorentzian Planck space. We take two probability measures, mu and nu, and when we do optimal transport, what we want is we first want to find transports from mu to nu, and then we want to associate a cost to a transport, and then we want to extremize this cost. Okay, so what is a transport between two measures? So classically, a transport in the point of view, so you have the point of view of Monge and of Kantorovich. So Monge tells you that a transport is a map such that the push forward of the first measure is the second measure. But then it is not true that for every mu and nu you always have a map. For instance, if mu is a delta and nu is not, you cannot have a map. And so Kantorovich relaxes this notion by saying, well, a transport is more generally, so a transport could split the measure of a point into many points, and it is more generally just a probability measure pi in the in x times x, such that the push forward on the first coordinate is your first measure mu, and the push forward on the second coordinate is your measure nu. Okay, so this is the classical point of view which is used in metric geometry. Okay, now since we are doing Lorentzian geometry, we are interested in not just any couple of points, but we are interested in the couple of points which are causally related. Okay, and so we are interested in doing transports which are compatible with this causal relation. So we want that we start from the measure mu, and we want that it is mapped into measure nu, such that such that the measure in x is mapped into maybe more than one point in the support of mu, but we want that these points in the support of nu are in the future of x. Okay, so that it is compatible with the physical picture. Okay, and so we introduce this class of transports, which are the causal transports, so pi less or equal, which are those transports which are concentrated on the causal relation. So pi of x2 less or equal is equal to 1, where x2 less or equal is the causal relation included in x times x. And then we have the subclass of timelike transports, which are those transports which are concentrated on the timelike points. Okay, so they concentrate into the set x squared less less, where x squared less less is the subset of x times x of points which are related with respect to the less less relation. Okay, so we have this kind of transports, and with them we can define the natural analog of the Wasserstein distance. Okay, so in order to do that, we have to take a transport, associate to it a cost. So we fix some p, some exponent p, and the cost is the time separation function 2 power p. So we integrate the time separation function to power p with respect to this plan. We take the 1 over p power. Okay. Now remember, as we recalled before, that in the Lorentzian setting you want to maximize the time separation function, while in the Riemann setting you want to minimize the distance. And so, since you're in the Lorentzian setting, you want to maximize. You want to take the sup of this cost. Okay. And now, since you want to take only transports which are compatible with the causal relation, you do the sup over the transport pi, which are causal. Okay. All right. So, and this is in case there exists at least one transport which is causal from mu to nu. If instead there is no causal transport, then you just define LP to be minus infinity. Okay. Now, if you're familiar with the Riemannian setting, in the Riemannian setting, typically you take p equal to 2, or actually any p bigger than 1. In the Lorentzian setting, instead, it is more natural to consider p less than 1. This is because of the convexity properties of the Lagrangian. It is convex under this frame in this regime, while in the Riemannian setting, it is convex in the regime p bigger than 1. And this is because of the Lorentzian signature. Okay, so this Lorentzian Wasserstein distance was already proposed in a paper a few years ago by Eckstein and Miller, and it satisfies some natural properties in the Lorentzian setting. For instance, it satisfies the reverse triangle inequality, as we saw before. So it is just a triangle inequality, but with the reverse sign. Okay. So basically, what you are doing is you are lifting. So with this P Lorentz Wasserstein distance, you have the Lorentzian geometry on your manifold, and you are lifting it at the level of probability measures. So you are lifting the Lorentzian distance at the level of probability measures. Okay, now some basic properties. Notice that here you are taking the soup over all the plans which are causal, and the set of causal plans is not as nice as the set of all plans. So it is convenient to reformulate the problem by taking the soup over all the plans, and the standard trick is to just modify your cost. So notice that if you set the cost to be equal to the old one when two points are causally related, and minus infinity otherwise, when you take the soup over all the plans, you are basically taking the soup only on the causal plans. Okay, so you can also see the LP distance by taking the soup over all the plans by this kind of massaged cost. Now, an important property is that under the assumption that I discussed before, so if X is globally hyperbolic, geodesic, and causally closed, then such a cost L is upper semi-continuous, and so one can apply the classical theory of optimal transport to get existence of an optimizer in the LP Lorentz Wasserstein distance. So this is the statement. So if X is causally closed, globally hyperbolic, you have two probability measures, mu and nu, which admit at least one causal coupling joining them, and they satisfy some natural interability condition, which is satisfied, for instance, if mu and nu have compact support. Then you always have an optimal coupling between them. So you always have an optimal causal coupling, which achieves equality in the definition of the Lorentz Wasserstein distance. Okay. So this part, so this is not hard, and this is kind of standard. Let me say, so it's going to be useful to introduce a little bit of notation. So I'm going to call pi p opt less mu nu the set of optimal plans which are timelike. Okay, so it's going to be very useful to consider those optimal plans which are timelike, meaning that for any 2 points x and y in the support of say pi is concentrated on timelike points x and y. Okay. So as we have seen, the existence of an optimal plan easily follows by direct method. And what is the rough idea of an optimal plan? Well, an optimal plan pi is roughly moving the mass mu at a point x into some suitable points in the support of mu. So you are possibly splitting the mass of at a point x in several points, but they are all but these points in the support of nu are all in the future of x. Now the basic question is which are such suitable points chosen by x, okay? Or better said, how can we detect a subset gamma in the causal relation such that the optimal plan pi is concentrated on gamma, Okay, so this is really a question which is at the heart of optimal transport, and it involves two key notions in optimal transport theory, which are cyclical monotonicity and Cantor-Lewis duality. So the basic idea is that a subset gamma is cyclically monotone with respect to a cost function C, if roughly it is optimal with respect to perturbation by finite many points. Okay, so you can change gamma at finite many points, and you want the new set to be less optimal than your gamma. Okay, so this is the kind of finite test to see if gamma is optimal. And Cantor-Lewis duality basically gives a recipe to construct cyclically monotone sets. So what happens is that in the Riemannian setting, Cantor-Lewis duality is very powerful, and indeed cyclical monotonicity is equivalent to optimality. Okay, so studying Cantor-Lewis duality is really key in the Riemannian setting. In the Lorentzian setting, Cantor-Lewis duality is much more subtle. Let me mention some previous work by Bertrand, Pratel-Impuel, by Lorentzian, and by McCann. And in general, optimality is not equivalent to cyclical monotonicity. So what is true is that optimality implies a cyclical monotonicity, but the other way around is much more tricky. What is the main difficulty is that the cost that you use in order to do things, in order to do optimal transport, is this L, which is infinite on a very large set. Okay, so optimal transport works very well for finite cost. If the cost is infinite on a small set, you can still do things. If the cost is infinite on a very large set, as it's in this case, then things are much more complicated. Okay, so in order to do that, in order to study optimality and the Cantor-Lewis duality, we have to detect the right set of measures which satisfy Cantor-Lewis duality. Okay, so this is why I'm going to define some notions. So I say that a couple of measures, a pair, mu nu of probability measures, is timelike p-dualizable by some plan pi. If pi is an optimal plan from mu to nu, which is also timelike, and if mu and nu satisfy some nice integrability condition. Now, this definition is non-empty. For instance, if x is globally hyperbolic, mu and nu have compact support, and there exists a timelike optimal coupling, then mu and nu are timelike p-dualizable. And this definition of timelike p-dualizable generalizes the notion of Q-separated by McCann, if you've seen the paper of McCann. So this is more general. Okay, so basically McCann works with the Q-separated measures, and we are able to work with this more general class of measures. Now, the reason for the previous definition is that Cantor-Lewis duality, the weak Cantor-Lewis duality, holds for timelike p-dualizable measures. Okay, so what is weak Cantor-Lewis duality is the following proposition. So let X a prime space with good properties. Then it happens that mu and nu, so the pair mu nu is timelike p-dualizable. Then weak Cantor-Lewis duality holds, meaning that you can write the sup in the definition of the Lorentz Wasserstein distance as an inf of a dual problem. And this dual problem is you take the inf of the integral of function u integrated with respect to mu, plus the integral of a function v integrated with respect to nu, where u and v are any functions which are in L1, such that their sum is in L1 of the tensor mu nu, and their sum is bigger or equal than the cost LP in the product of the supports. Okay, so this is the classical. So this is the kind of the adapted notion of weak Cantor-Lewis duality to the Lorentzian setting, and so this holds quite in general. strong control of duality, so strong control of each duality instead asks for existence of solutions of the dual problem. So it asks for existence of optimal functions in the right-hand side here, achieving the inf. It is much more subtle. In general, it is not true. It is in the Lorentzian setting, due to this infinite cost, it is quite rare that you have this strong control of duality. And it is linked to cyclical monotonicity of plans with respect to the tau p cost. So what we can prove is that if there exists a tau p cyclically monotone plan, then strong control of duality holds. Okay. But for the rest of the talk, I would like you to remember this notion of timelike p-dualizable. So this timelike p-dualizable means that you have an optimal plan between mu and nu, which is timelike, and you have nice intermediate condition. This is enough for the rest of the talk. If you want to a little more of information, this notion is natural because it is enough in order to have weak control duality. Okay. Now, for the rest of the talk, I would also need a little stronger notion, which is the one of strongly timelike p-dualizable. So a pair is strongly timelike p-dualizable if it is timelike p-dualizable, and basically any optimal plan is timelike. Okay. So I asked that there exists a subset gamma in the containing the timelike set intersect with support of mu times support of nu, such that any causal plan is optimal even only if it is concentrated on this set gamma. Okay, so this set gamma is the maximal set which contains where all the optimal plans are concentrated. And again, the definition is non-empty because it is easy to construct examples. Okay. Now, so we have seen the notion of, we have seen the notion of optimal transport in the Lorentzian setting, the p-dualizability, and the weak control duality. Now, it is useful to understand also geodesics in the Lorentzian Wasserstein setting. Okay, so the point is that once we have that the underlying space is geodesic, then we can lift the geodesic structure also at the level of probability measure, so at the level of Lorentz Wasserstein distance. So we say that we have a Lorentzian planning space. We say that a curve of probability measures is an LP geodesic if and only if the LP distance between mu s and mu t is equal to t minus s LP distance from mu0 to mu1. So notice that in particular, these LP geodesics are implicitly causal and future directed, okay? Because this LP is already the time flowing included. And the basic property of these geodesics is that if you're in a nice space, so globally hyperbolic and geodesics, if you have two probability measures, mu0 and mu1, which are of compact support, and such that there exists at least one optimal plan with the support contained in the timelike relation, then you always have an LP geodesic joining mu0 and mu1. So the existence of LP geodesics joining two measures which are causally related is quite general. And you can always represent a geodesic with a probability measure defined on the space of continuous causal curves by saying that you have a probability measure eta on the space of continuous curves, such that the push forward via the evaluation map is equal to mu t. So this is a so-called dynamical optimal plan. And what happens is that the optimal transport, so for almost every gamma, so for eta almost every curve, this curve gamma is a geodesic from gamma naught to gamma 1, where gamma naught is in the support of mu0 and gamma 1 is in the support of mu1, meaning that the LP optimal transport is performed along geodesics of the underlying space. Okay, so the picture to have in mind is the following one. So here you have the support of mu0 inside X. Here you have the support of mu1 inside X. Here I'm picturing timelike geodesics, which goes from support of mu0 to support of mu1. So since they are timelike, you see here that their velocity is always inside the future cones. And what happens is that the support of mu1/2 is concentrated at 1/2 midpoints of geodesics from support of mu0 to support of mu1. Okay, so this is the dynamical picture. Okay, now the characterization of lower bounds on the timelike Ricci. Let me start with the smooth setting. Okay, so as for the Riemannian setting, a key object is the entropy. So in order to have an entropy, in order to have a well-defined entropy, we have to fix a reference ambient measure M. Okay. Now the entropy of a probability measure mu with respect to the reference measure M is by definition the integral of rho log rho in the M, where rho is the density of the probability measure mu with respect to reference measure M. And if this is non-interable, or if mu is not absolutely continuous, we set the entropy to be plus infinity. Okay. Now the following theorem. In the next statement, I want to recall the characterization of the lower bounds on the Ricci. So the first place where lower bounds on the timelike Ricci, the orthogonal transport appeared is in a paper of McCann, who characterized the lower bound by 0. Then a few weeks later, with Suhr, we posted a general lower bound, general upper bound, also by a tensor. And now let me give the statement which appeared in the paper with Cavalletti, where we use this quite general setting of p-dualizable measures. Okay, so this statement, as I recall here, is in the paper with Cavalletti, but is based on previous works, as I said. Okay, let M and G be a globally hyperbolic spacetime, fix p between 0 and 1, then the following are equivalent. First property. Ricci curvature evaluated at a vector, a timelike vector v, is bigger or equal than minus k GVV, and this is for every timelike vector. So this is a timelike Ricci curvature lower bound, because timelike is because you are testing it over timelike vectors. Second condition, for any couple, for any pair of probability measures, which are in the domain of the entropy, which are timelike p-dualizable. Time-dualizable, remember, it means that you have an optimal coupling which is concentrated on the timelike set, and they have a natural integrability condition. So for any pair, you have there exists an LP geodesic mu t joining them, and such that the entropy along this geodesic has nice convexity properties. So more precisely, you ask that the map T, which goes from 0, 1 to R, which gives the entropy of mu T with respect to vol G, is semi-convex in this local Lipschitz, and it satisfies that the second derivative in a weak sense minus 1/2 first derivative squared, which makes sense almost everywhere because the E is local Lipschitz, is bigger or equal than K, which is your lower bound on the Ricci, times the integral of the time separation function tau with respect to the optimal coupling pi. And you ask this to make sense in the distributional sense. Now notice that if K is equal to 0, you have second derivative of the entropy minus something positive bigger or equal than 0. So if you also throw away this which is making the inequality stronger, this in particular is implying that the entropy is convex along timelike geodesics. Okay, but if K is equal to 0, this n term is making the inequality stronger, and this K, if K is bigger than 0, is stronger than convexity. If K is less than 0, is weaker than convexity. Okay, so property 2 is for any timelike redualizable, and the property 3 asks the same convexity condition, but for a smaller set of probability measures. So for any couple of probability measures which are in domain of the entropy, they are of compact support and which are strongly timelike redualizable. So strongly timelike, remember, that means that any optimal coupling is timelike. Okay, so what is proved is that these three conditions are equivalent. Okay, so it is equivalent to have lower bound on the timelike Ricci, convexity of the entropy among geodesics joining timelike redualizable measures, and convexity of along geodesics along strongly timelike redualizable measures. Okay, now as in the Riemannian setting, the goal, so why one writes down such a theorem, is because this characterization makes sense in a low regularity setting, and so one can define a synthetic lower Ricci curvature bound in the timelike direction by taking 2 and 3, 2 or 3 as a definition. If you take 2 as a definition, you get the so-called timelike CDKN condition. If you take 3 as definition, which was testing the convexity property over a smaller set of measures, which are the ones which are strongly timelike, you get the so-called weak timelike CD condition. Okay, here I just repeat the statement. One can also skip it. So you can also give an alternative definition using another entropy, and this alternative definition is integral, so it does not involve derivative. But you are welcome to see the slides. Now I am running out of time. If you consider just the case of second measure mu1 to be a delta measure, then you have the so-called timelike MCP, okay, which is this condition here, which is basically the same as before, just with the second measure to be just a delta measure. This is weaker than the other. It corresponds to the Lorentzian analog of the measure contraction property, which was pioneered in the Riemannian setting, in the metric setting by Sturm and Hota. And what happens here also is that the weak timelike CD implies the timelike MCP. Then what happens is that timelike MCP imply, which is the weakest of the notions, imply Bishop-Gromov inequality in the timelike direction, implies Bonnet-Myers inequality in the timelike direction, and existence of optimal maths. So you can solve the Monge problem assuming the timelike MCP. If you assume more strongly the weak timelike CD, then you have the Brun-Minkowski inequality in the timelike direction and in a sharp form, which is sharp even for model spaces in the Lorentzian manifold, which are de Sitter and anti-de Sitter. You have sharp Bishop-Gromov inequality, which are again sharp in the de Sitter and anti-de Sitter, and sharp Bonnet-Myers inequality. Okay. Now a key feature. Now how much time do you have? Another couple of minutes? Yeah. So I would just say what are the states. So I would just say what are the results without entering into the details. Okay. So let me just state that in the Lorentzian setting, we also have a kind of a notion of convergence of Lorentzian Pareil spaces, which mimics the notion of Gromov-Lott-Sturm-Villani convergence that we have seen last week, and more precisely the pointed measure of convergence that I discussed in my first lecture. Okay, so there is a natural analog in the Lorentzian setting, And we proved the stability of these notions of timelike MCP and of CD under this condition. So timelike MCP is really stable. Timelike CD is a bit more subtle in the sense that if you have a sequence of timelike CD, they will converge to a weak timelike CD. So if you're interested, I'm happy to discuss about that in the questions. But in any case, this is good enough in the sense that if you have smooth manifolds, they satisfy. So if you have smooth manifolds, which are of dimension n, with timelike Ricci bounded below by minus k, they are timelike CD, and so their limit is going to be weak timelike CD. And actually, all the inequalities that we proved are sharp already for weak timelike CD. So weak timelike CD is good enough in order to study limits. And then we also prove a synthetic version of the Hawking singularity theorem, which basically says that if you have a timelike MCP space, which admits a kind of Cauchy hypersurface, which has some good bounds on the mean curvature. So you basically need the mean curvature to be negative enough in the timelike direction, and there is an interplay between how negative the mean curvature must be depending on the lower bound on the Ricci curvature, on the timelike Ricci curvature. Then your manifold is incomplete. Then there is a maximal time that geodesics shooting from this Cauchy hypersurface can travel. Okay, so this is a timelike incompleteness theorem, which generalizes to the synthetic setting a celebrated result by Hawking. So sorry for being late and for running, and thank you for your attention.
Thank you, Andrea. Is there a question?
Yes, I have a question. Does there exist a Fourier theorem for this kind of optimal transport in Lorentzian manifolds?
Fourier theorem, you mean the existence of optimal maps?
Yes, with some convexity properties.
Yeah. So so the answer is yes. So there is an analog. So there is an analog of the kind of Brenier-McCann, I would say, in the sense that in the smooth Lorentzian setting, McCann proved the existence of optimal maps for the cost p between 0 and 1, and the proof mimics, say, his proof, the existence of a Brenier-McCann map in the Riemannian setting. The existence of a Brenier map is also true in the synthetic setting, and this was proved in the paper of Cavalletti and myself, under the assumption that the synthetic space is timelike non-branching. So you want that the geodesic, which are timelike, do not branch, and that the space satisfies the timelike MCP condition. So the answer is yes. So you have the existence of a Brenier map for the p cost for p between 0 and 1. If the two measures are causally related with the plan which is timelike, under quite general condition on the space.
There is a question in the chat.
Okay, so let's see. Okay, yet another variant called delta. What was on purpose? So where is delta?
No.
Okay, maybe this direct. Okay, can you say a word about the Hawking singularity theorem that you mentioned in the abstract? Yes. So the Hawking singularity theorem is here. So maybe I shall go a bit slower. Okay. So the Hawking singularity theorem is basically saying that if you have a globally hyperbolic spacetime, okay, with a lower bound on the Ricci. So say for simplicity that you have that the timelike Ricci curvature is non-negative, okay? And you assume that your space-time has a Cauchy hypersurface with negative mean curvature, or more precisely with mean curvature in the future directed normal is bounded above by a negative constant. Okay, so under these assumptions, Hawking proved that there exists at least one geodesic which is which ends in finite time. Okay, so that so this means that your manifold, your Lorentzian space, is timelike, geodesically incomplete. Okay, and so this is the classical result of Hawking, which was then generalized to any lower bound on the Ricci, on the timelike Ricci, provided that the mean curvature is negative enough. And this was generalized to C11 and I think up to C1 metrics by the Vienna school. So here we mention Kunzinger, Seemann, Graf. There are a bunch of people working in this field, and basically the idea is to approximate your metric of low regularity with the smooth metrics, do the proof in the smooth, do the smooth proof, and then go via approximation. And instead, our approach is synthetic. So we proved we extended the Hawking singularity theorem to the synthetic framework of Lorentzian prelength spaces with the timelike MCP condition. And yeah, and the conclusion is still that that the space is timelike geodesically incomplete. So any more questions? Should I go more in detail?
So can I ask another question?
Sure, Alexander. Yeah.
So it's related to what you just said. So I think people in this Lorentzian theories, so they usually, so if they try to go beyond smoothness, so they use some distributional notion of Ricci curvature bounds. So does your synthetic notion covers this?
Right. So this is currently under investigation. I think so, in the sense that I think that it could be, to answer this question, it is useful to use the stability, in the sense that we prove that our notion is stable under convergence. So the point that since they agree, since this notion agree with the smooth one, if you approximate, say, both the distributional one and ours with the smooth solution, they should agree also when they are not smooth. But there's some work to be done. So yeah.
But I think, I mean, so their notion, so is more or less something like this, so that that you can approximate your metric by smooth metrics, such that the Ricci curvature is not bounded by a constant, but is bounded in one sense or something like this by the same constant. So does your theory isn't stable enough for that?
Right. So for that, one should need to refine the theory. So if you don't have a lower bound by a constant, then say our stability is not enough, say strictly speaking. But at least in the metric setting, there is some very interesting result in this direction by Sturm and the Bonn school, who are able to handle lower bounds on the Ricci by a measure, by a radon measure. And so I am confident that, say, with a lot of work, something can be done also in the Lorentzian setting.
Thanks.
Thank you.
Another question? No. So thank you, Andrea.
Thank you very much for your attention and for the questions.
Thank you. Bye-bye. Bye.